Hello, this is Jennifer Martinez, and in this video we're going to talk about alternate notations for the second derivative and what that second derivative tells us. The second derivative is the derivative of its derivative. And so, since that is true, the derivative itself is a function, and that's why we can consider its derivative. So for a function f, the derivative of its derivative is called the second derivative, as we saw in the last video. It can be written as f double prime or y double prime, where y is equal to f of x. So let's go over the alternate notation. So if you remember, but first I'll do the first derivative. If you remember, y prime is the same as f prime, and we came up with its other notation called dy dx. This, by the way, is the derivative. One of the reasons they do this is the derivative with respect to y. Is another way that they look at that, because that's what we're going to look at for second derivatives. So y double prime, which we know is f of x double prime, that's going to be d dx, the derivative of the derivative. So what they do is they're going to call this d squared y over dx squared. That is our new notation of the second derivative. And if you ever need a higher derivative than the second derivative, it would be the same. The derivative of the second derivative is called the third derivative. And that's going to be d cubed y over dx cubed. Or in general, if you ... a lot of times they'll say the nth derivative. They put a little parentheses there, not to confuse it to raising to the n power. And that is going to be dn dx is the notation that they will use. That is because we are taking the derivative of the derivative. So the d is what the exponent is and the whole dx squared. So what does the second derivative tell us? So we saw in the video before, the first derivative is like velocity, so the second derivative is like acceleration. What does it mean when the second derivative is negative? What does it mean when the second derivative is positive? So to answer that, let's look at the first derivatives first to remind us about that. So if the first derivative is positive, that means that the original f, if you remember, this is like the slope, the dy dx, of the tangent line. And as we go up, that means that f is going to be increasing. It does make sense, because if I draw something that has positive slope, that means that you must have an increasing function. If f is negative, when is f negative? Then that means that the f is decreasing. Like maybe on this side of the graph. So here f prime is positive because f is increasing. F prime is negative because it's decreasing. The slope of the tangent line would be positive here, and on the left side, the slope of the tangent line would be negative. And you can make this an if and only if statement as long as the derivative does exist. So if you have an increasing function and the derivative exists, then the derivative is always going to be positive over here. And on the left side there, if you have a decreasing function and the derivative exists, if you just add an extra statement, then the derivative is going to be negative on the left. So now let's look at second derivative. If f double prime is bigger than 0, from above here, it's one level down, f prime, that means f prime is increasing. That makes sense. So what does it mean for a derivative to be increasing? Well, if you look at our picture, as we choose different values here, you can see here that the derivative is a little smaller here than it is there. So in this case right there, it is increasing. You can see that what happens when a derivative is increasing, it kind of bends the graph, bends upwards. That is called concave up. Concave up is like an upward bowl. Believe it or not, even the left side where it's decreasing, it is still concave up. Because if you look at this slope, that is steeper. Maybe it's like, I don't know, -2, and maybe this one is -1, right? Those derivatives, -1 is larger than -2, so that is still increasing. So you see, even on the left, it's kind of like an upward bowl shape. It bends up. And we can see here that if it's negative, that means from above that f prime is decreasing. So the original f was probably concave down. So let's check that out by looking at this function. So here you can see that as we go left to right, those slopes are going to be decreasing. So it's going to be bending down is what happens to those. So f is concave down. Even over here, you say to yourself, well, that's like maybe -1. Maybe that's like -2. Those are getting smaller. So as the derivatives are getting smaller, as they're decreasing, f is concave down. So on the left, we'll call this A. We see that f is positive. It doesn't matter what f prime is. It could be positive, or on the right, it's negative. But still, the second derivative is negative everywhere. And the same with the one above. You can see that on the left of 0, it's negative. On the right, the first derivative is negative. The right of 0, the first derivative is positive. But the second derivative is positive everywhere right there. So it talks about the concavity. So let's look at example 3. It says a population growing at a confined environment often follows a logistics curve like the one shown in 2.49. Relate the sign of the second derivative to how the rate of growth, the first derivative, changes over time. And what are the practical meanings of that T0 and the L? Okay, so if you notice here, this is O is increasing, right? dp dt is O is positive. It's positive everywhere. O is increasing. The slope is O is positive. But the second derivative, notice how it's concave up in the first bit and then it's concave down. So here, the second derivative, just use that notation, is a positive, and over here, the second derivative is negative. It does make sense because the derivative of the derivative, it gets steeper and steeper, and then it kind of slows down. So in the beginning, it looks like the population is like an exponential growth. It's rapidly growing. But then there's a time that it can start slowing down. Looks like a decay, doesn't it? So again, the second derivative is positive for t smaller than t0, and the second derivative is negative for t larger than t0. So what is going on right at t0 there? It looks like where it changes from concave up to concave down. So if you notice, right, let's look at the rate of change. So let's relate the rate of change to the second derivative at that point. If we look at this, it's increasing, and then it starts slowing down. So it looks as if that's where the derivative is at a maximum. So if we look at the solution, when in the book, when t is less than t0, it says that the derivative is increasing and the second derivative is also increasing. We had that. Right at t0, what happens is the derivative is at a maximum. In other words, t0 The population is growing at the fastest rate at that spot. And then it starts slowing down. For t bigger than t naught, the rate of growth p of t is starting to decrease. So that means that the derivative is a negative. At t naught, the curve changes from concave up to concave down. We said that. And by the way, we didn't say that. The second derivative, let's write that down, d is equal to 0. Right? It changes from positive to negative. So that's where it's going to be equal to 0. They call that an inflection point. The inflection point is going to be the place where it goes from concave up to concave down. You do have to be careful because sometimes inflection points, it's not just necessary where it's equal to 0. Sometimes inflection points, they'll be equal to 0. The second derivative would be equal to 0, that is. But on the left side, it still could be concave up. And on the right side, it would also be concave up. So you do have to be careful. It's not necessarily the place where it's equal to 0. The definition of inflection point is where it changes concavity, where it goes from concave up to concave down. We'll see some examples, more examples on this in the next chapter. And actually, we're going to see this in chapter 4. I just looked it up. Inflection point is where f changes concavity, and that won't be really introduced in the book until chapter 4. What is the practical meaning of L? Well, L is going to be the limiting value of the population, right? That's where it's going to limit off as t goes to infinity. Biologists, by the way, call the carrying capacity, the carrying capacity of the environment. So let's just try one more example, a problem from the book. This table gives the number of passenger cars in millions. They have that this is the place where they got this information. So it's an actual application in US in the year T. So what do we think? Do f prime and f double prime appear to be positive or negative during the interval of 1975 to 1990, that interval? Well, we can see easily that the derivative is positive because if we look at the f's from this interval, we see that they're getting larger. They are increasing. After 1990, they start decreasing. So part B, we can actually do that now. F prime is negative during 1990. Oh, just to 2000, because it increases again, doesn't it, during that period. What about the second derivative? Well, do the second derivatives, we really need to look at what's the first derivative's doing. So I'm going to check this out. And I'm just going to look to the right of 1975 here and look at the average rate of change. So that 121.6 minus 106.7 divided by the 5. Can we do the same thing here? Next interval. And you can see that that would be 127 minus 121.6 over that 5. And I did again the third interval at the same time, 133 minus 127. So I looked at these three intervals divided by 5. You can see that these are decreasing. So because these are decreasing, f double prime is going to be negative. So let's continue the process to look at what f double prime is doing after 1990. So we'll just look at 1990. And again, I'm going to do the same thing to the right. I'm going to look at 1990 and then 1995. So doing the same thing here, we would have that the first one is negative. Oh, that one's negative 0.06 and then positive. But we want to know what's happening here. You can see it goes from a negative to a positive. So it looks like f double prime is actually appears to be increasing. From the data that we have, I realize that this is limited. There's 5 years in between, so a lot of fluctuation could be happening in between. But overall, from this data, it appears that the second derivative is positive. So you might be thinking that we're going the other way around from what I wrote above. But if you look at the last statement in the book, you can go the other round. This can be an if and if as long as f double prime exists. The f is, if f has concave up, then the derivative is positive as long as f double prime exists.